So Remy, are you the president?
Yes.
Okay.
Yeah. There has been a confirmation of what you wrote on your manuscript.
Yeah.
Something that was not confirmed is that, I mean, you were, the plan was that you would come to Lyon to defend. Eventually, you defend at IMT.
Yeah.
And I think I'd like to wait so that we start sharp, because probably some people will not join the YouTube stream before.
Yeah, sure.
Before the right time.
Ok, moi je vais vous laisser sur Zoom, ça marche bien sur YouTube, là, je viens de regarder.
Thank you, Pierre.
Merci. Merci, Pierre. Vincent, do you have coffee ready?
I had it just before, actually.
So just imagine the crowd, like in a real room, but even better. People having their coffee and ready to listen to you.
Is it to lower the stress or to
increase the stress? More comfortable. Your friends are listening.
Yeah.
Okay, I think it's we are on time, and so I'm Rémi Gribonval, research director with INRIA at École Normale Supérieure de Lyon, and the jury designated me to be the president of this session. So Vincent Gripon, you will have 45 minutes to present your work, your research, or your projects for this habilitation defense in front of a jury composed of Sophie Achard, who is a senior research scientist with CNRS in Grenoble, Pascal Frossard, who is a professor at École Polytechnique Fédérale de Lausanne, Julie Grolier, who is a senior research scientist with CNRS Thales, Sébastien Lefebvre, who is a professor at the Université Bretagne Sud, and Antonio Ortega, professor at University of Southern California, who is attending from the US with a huge time difference, and he's I think it's 7 a.m. for him. So Vincent, it's the floor is yours.
So thank you, Mr. President. Thank you, members of the jury. Thank you to everyone who is attending to this presentation right now. Welcome to ENS Lyon. I'm very sorry that we could not make it in person, but considering the situation, the only option was to make it online. Can you see my screen right now?
Yes.
Okay. So I'm going to present to you my defense for habilitation en dirigé des recherches. Mainly when I ask people around me what I should present, I had different answers, but I tried to make a mix. So I will have a very brief first part where I will go through the quantitative aspects about my experience. In the second part, I will really go deeper into the scientific contributions, trying to highlight the past work. In the third part, I will discuss where my research is heading and future work, and I will have a very brief summary slide in the end. So to recapitulate, the timeline starts in 2008, because basically at that time I obtained my Master of Science from INS Paris-Saclay. After that, I started my PhD under the supervision of Claude Béraud with IMT Atlantique, and I was mostly working in the field of indexing. After my PhD, I went to McGill for a one-year postdoc, where I was co-supervised by Warren Gross and Michael Rabat. And what happened actually is that after I left France, Claude Bérou writes an IRC grant proposal that he obtained, and the project started in September 2012. So I came back to France to participate to the project, first as a postdoc, but then I became a permanent researcher, what I am still today. So what I wanted to emphasize on this figure is the fact that with the years, I've been involved in more and more domains of science. And right now, I would say that my work is mostly between signal processing, electrical engineering, machine learning, and indexing. Now, I also want to mention that I've been an invited professor with University of Montreal, where I was hosted by Yoshua Benjo during 1 year from 2018 to 2019. And this year, I've been a chair of excellence at Université Côte d'Azur, hosted by Professor Benoît Miramont. Now, in terms of supervisions, so I've supervised 8 PhD students who defended and 4 who are still in PhD right now. So Roti obtained twice the Best PhD Award. And I think it's more interesting to look at what they became. So it's quite diverse. For example, one of them is now a professor, another one is a teacher. The other ones, some of them are still postdoc, and others are working in private companies. So I like this diversity because it really shows that when you do a PhD in engineering, you can have a lot of different continuation. In terms of postdocs, so 4 of my postdocs have finished their contract. 3 of them are now professors. And the last one, Mathilde, she decided to stop doing research. She's now the Fab Lab manager with IMT Atlantic. In terms of funding, I didn't know exactly what to put in the slide. So it's kind of a very broad overview. I mainly separated public and private funding. And here you have the list of projects. So the width is the duration, the height is the amount of money. And what I found interesting is that on this figure, we clearly see that I mostly started with public funding, which is not very surprising because at that time I was mostly interested in very fundamental problems about storing information in neural networks. But now I have kind of a mix of fundings between private and public partners. And it can be explained by the fact that most of my research is aligned with applied problems like machine learning, for example. Now to finish about this quantitative aspect, so this is the number of publications for each year since 2008, separated in journals, conferences, preprints, and at the top of the columns, I've put the number of plenary talks I was invited to give. So in terms of impact, this is the number of citations per year, so it's growing, and I hope that if we continue to grow that way. So that's all for the very quantitative aspects about my CV. And now let me switch to more interesting parts about the scientific contributions. So in the manuscript, I tried to organize the contribution in 3 parts. Of course, this is not how it was done in practice, but I think it's simpler to do it that way. So I'll try to do the same here. And I will start with talking about my contribution with respect to graphs and graph signals. So just a recap first. When we talk about graphs, we mainly talk about tuples that are made of a set of vertices that have to be countable and a set of edges. And when we talk about graphs, normally, we do not make any distinction between an edge UV and an edge VU. If we want to have an orientation in the graph, we talked about directed graph or digraphs, and then the edge UV is different from VU. A very common way to represent a graph is by using its adjacency matrix A, which is basically the edge indicator matrix of the graph. Another important matrix is a degree matrix, which is a diagonal matrix where you put on the diagonal the number of edges a vertex is part of. A natural extension of graphs are weighted graphs, in which you can basically introduce them as seeing the adjacency matrix as not being 0 and 1s anymore. It can take any non-negative value, and basically the magnitude accounts for the corresponding strengths between the 2 vertices. So a common depiction of a graph is here, where you see the vertices depicted as circles and the straight lines that correspond to the edges. Now, another important notion for the talk is that of graph signals. So a graph signal is basically a collection of scalar values, one for each vertex in the graph. So a common way to represent it is by using a vector indexed by the vertices. There's a very simple way to connect a graph signal with the underlying graph structure through the notion of graph smoothness. So to introduce graph smoothness, first I have to introduce the Laplacian of the graph, which is a subtraction of the degree matrix and the adjacency matrix. And then the smoothness is simply defined as being the quadratic form of the Laplacian. So another way to look at it is with the equation below, where you see that basically it's a non-negative value. that is going to be close to 0 if and only if, when you have a strong connection between the vertices u and v, the values of the signal are very similar. So for example, here, I've drawn a graph signal that is smooth on the graph because basically you have small variations across the edges. And here is an example of a signal that is non-smooth on the graph because you have sharp transitions. Another important notion for the talk is that of graph Fourier transform. So one way to introduce the graph Fourier transform is by taking the Laplacian. And the Laplacian is a real-valued symmetric matrix, so you can basically write it as f lambda f transpose, where if f is orthonormal and lambda is diagonal. And you can make the arbitrary choice of having the values in lambda to be in ascending order. Now, if you do that, and if you take a signal x on the graph, you can express it in a basis where the Laplacian is diagonal. And if you do that, we call that the graph Fourier transform of the signal x. So the reason why we call that a graph Fourier transform is because basically, if you take the special example of an oriented ring graph, the corresponding matrix A here is the second matrix there, then you have exactly the fact that the graph Fourier transform matches the classical Fourier transform. So the rationale behind the graph signal processing framework and the graph Fourier transform is that if you take another graph structure, a generic graph structure, if you compute this matrix F, if you express the signal in a basis where the Laplacian is diagonal, sorry, then you have a natural extension of the Fourier transform for this specific domain. And then you can do a lot of interesting things, like, for example, defining convolutions that are simple pointwise multiplication in the Fourier domain. You can do translations by, for example, convolving with Diracs. And you can have this very nice expression of the smoothness, where you see that smoothness is basically looking at how much of the energy of the signal is aligned with the first eigenvectors of the Laplacian. So in terms of contributions, one example of a contribution we had in the past with respect to graph signals was to try to propose alternative definition for translation of graph signals. So the reason why we wanted to propose alternative definition is motivated on the left here, because you see, basically, if you take an image can be seen as a graph signal, as seen in part B here, where the graph is not depicted, but it's a grid graph. So basically, we connect a vertex to its neighbor vertices. Now, if we try to translate the signal on the graph structure, we obtain the kind of signals that are at the bottom. And as you can see, it's kind of a mix between a translation and a low-pass filter. So this is somehow problematic because when we talk about the graph signal processing framework, we really see it as a generalization of the Fourier transform to irregular domains. But the problem is that even for very regular structures, if they are not 1D, it's not clear that there's this analogy between what we expect the translation to be and what it is actually. So we came up with these alternative definitions of translations of graph signals that have this good property of matching exactly what you would expect if you have a very regular grid structure. Another example of a contribution related to graph signal processing is about the graph uncertainty principle. So just to recall first, in classical signal processing, the uncertainty principle states that you cannot have a signal that is at the same time time-limited and frequency limited. Now, authors have been interested in trying to see if such a result can be expressed for graph signals. So for example, in an influential paper in 2012, Agaskar and Liu introduced the notion of graph spread, so around the vertex U, which is simply looking at how much of the energy of the signal is far away from you in the graph. Far away is measured using the geodesic distance. The spectral spread they introduce is simply the smoothness. And now in their paper, they show that for some specific graph structures, you cannot have both these quantities arbitrarily close to 0 for the same signal. So for example, a contribution we had was last year in a book chapter where we were interested in trying to generalize these definitions, because we were a bit concerned about the fact that in their definitions, you have to consider a central vertex U. And for the spectral spread, basically, it's like considering a central frequency, which is 0, because as I said before, smoothness is basically measuring how well the signal is aligned with the first eigenvectors of the Laplacian. So we came up with this generalization where we look at all possible central vertex U, and we look at every possible central frequency I. So it's a bit more complex to analyze, but we were still able to obtain the following results. With ring graphs, which are very regular graphs, we have an uncertainty principle in the sense that it's not possible to find a signal that is at the same time with a low graph spread and a low spectral spread, even if the number of vertices tends to infinity. But for other types of graphs, like star graphs, which are kind of degenerate graphs, where you have one vertex which is connected to all the other vertices, you can have such signals that are arbitrarily close to 0 in terms of graph spread and spectral spread. Another question that we found of interest is in many cases, you have signals, you know that they have some underlying structure, but you don't have explicit access to this structure. So you cannot deploy the framework of graph signal processing. Now, what you would like to do is you would like to find a graph structure that matches your signals so that you can then use the tools for graph signal processing. So mainly the question is, how are you going to relate your signals to the graph structure? And in 2016, later in 2017, we came with this idea of saying that maybe we could consider that the signals we are observing were initially white, but they were colored by multiplication by polynomials of the adjacency matrix of the graph. It's interesting because if you do that, the covariance matrix of your signals is going to have the same eigenvectors as the adjacency matrix of the graph. So provided you have enough observation and you have a fair estimation of the covariance matrix, you know the eigenvectors of the adjacency matrix of the graph, and you only don't know the eigenvalues. But because you know it's a graph structure, you know that when you're going to combine the eigenvalues and the eigenvectors, you would like the coefficients to be non-negative, and that defines the polytope of possible solutions. Now, any point inside this polytope is a potential candidate. You can find one that has a specific property you're looking for, like sparsity, for example. Another paper I wanted to mention, even though it's not really graph signal processing, is a contribution I had during my postdoc in McGill with Mike Rabat. And the hypothesis we had at that time was that the signals we are observing are basically a subset of vertices for which there exists an underlying path connecting them in the graph. So we don't observe the path, but we know that the vertices belong to a path. And interestingly, in the paper, we were able to show that if we observe all such subset of vertices for a length 3, we can retrieve the graph structure for if we have necessary insertion conditions for the graph to retrieve uniquely its structure. So it's quite a nice theoretical result. Of course, we were also interested in applications of these methods. And one example is what Mathilde Ménoret did during her postdoc. And this is an extract from a paper where we were interested in brain decoding. So the experience is the following. You have a subject, he's looking at an image on the screen, and we record the brain activity. So it's using a fMRI here. And the question is, can you guess what is the category of the image based on the brain activity? And we wanted to use graph signal processing to try to improve the performance of methods deployed in that condition. And for example, here you see that we tested multiple graph structures that we inferred from the signals and multiple ways to leverage the graph structure, for example, using low pass filter, high pass filter, or graph sampling techniques. An interesting finding was that the best results were obtained with graph structures that are semi-local. And what it means is that it combines two types of information. The first one is about the statistical similarity between the signals that are observed in regions of interest in the brain. And the second one is about the proximity using the GPS coordinates of the centroids of these regions of interest. Another example of a contribution was during the PhD of Alan Aboudib, and he was interested in the problem of bottom-up visual attention. So the problem is the following. You have raw images, and you would like to obtain what we have in the middle here, which are what we call saliency maps, which is basically a probability distribution trying to predict where a human eye is going to look at when he's going to look at this image. So we have the ground truth, and we have algorithms. We compare what we obtain, and we want the best possible precision. So what Alan did during his PhD is that he came up with some elements coming from the literature on the retina, the biological retina. And in particular, we know that there's not the same density of sensors close to the fovea or close to the periphery. And we know that they do not observe the same spectrum of values from the images. So we came up with this model that is very close to what we know the retina is processing, and we just plugged it into a classical baseline method. And interestingly, the method ranks first for a few months on the classical benchmark in the field, which is the MIT Saliency benchmark. And we were eventually beaten, but only by methods that were relying on data-driven approaches, so using a lot of data to train machine learning approaches. So now I want to highlight some contributions with respect to using neural networks for indexing. So first, let me just explain roughly what we're talking about here. So indexing, you could see it as the following problem. You have a collection of data elements, and these data elements typically have vectors. And there are two types of problems we are interested in. The first one is the exact match problem, where we have a prop vector. We want to know if the vector is part of the collection or not. So it's set membership test. And the other one is the approximate match problem, where we want to find the data elements in the data collections that are the closest to the probe. Now, a very good model to try to solve that are associative memories. Associative memories are basically neural networks, and they are efficient because they offer a good compromise between the accuracy of the solution and the complexity in terms of number of operations. So for example, a very common model is that of hop field. So the hypothesis here is that the data elements are binary vectors -1 + 1. You're going to compute the matrix W, the gram matrix. And then the retrieval procedure is as follows. So you take your initial vector, you multiply by the matrix, you look at the sign of the values, and you iterate. And you hopefully will converge to the closest elements in the dataset. Another model is the Wilshire model, which is very similar, but now you have vectors that are 0, 1, and they are sparse. And because they are sparse, you can compute the gram matrix, but in a different algebra. So basically here, you don't have a summation, but a maximum. And now the retrieval procedure is a bit different because you have a thresholding that is not necessarily 0. It's a threshold value that has to be found in practice. So when I started my PhD, actually, hop field and Wilshire network already existed, but it was known for quite a while that their efficiency was asymptotically 0. The efficiency measures the entropy of what you store compared to the amount of material you need to represent the network itself. So for hop field, it was proven by McEllis in the 90s. For Wilshire, there was some proofs, but they were not necessarily mathematically correct, but there were strong evidence that probably the asymptotical efficiency was 0. And we came up with a proof in 2017 with the help of mathematician colleagues to actually prove that the efficiency was asymptotically 0. So during the PhD, we came up with the strategy of trying to add some structure to the data elements we're going to store. And the structure consists in considering that we're going to have only one non-zero element per subvector. So we split the data elements in subvectors. There's only one in each subpart. Now, the storing procedure is the same as the Wilshire network, but then we can leverage this specific structure when we want to retrieve the closest match. There are two ways we can do that. We can replace the matrix product by slightly different operator. I'm not going to get into the details now. But we can also replace the nonlinear function by a local winner takes all. So we don't have one threshold to be applied to the whole network, but we have one threshold per subsection of the network. Interestingly, you can, under some mild conditions, re-express these operations to be fully binary. And that was something that we used to make some efficient hardware implementation of this system. I'm going to give some examples afterwards. Now, in terms of performance, you have an example here of a drawing where typically we look at the error rate, so the probability that we do not find the closest match when we are given a probe, as a function of the number of elements we stored in different memories. So we compare the hop field system with the Wilshire system. And as you can see, going from hop field to Wilshire, so basically replacing the summation by a maximum and replacing the nonlinear operators, we can roughly double the number of messages we can store for the same error rate. Now, using the structure that we propose during the PhD, you can see that we have a huge gain in terms of number of messages we can store. Of course, this comes at the cost that the messages we store, when they are constrained this way, carry less entropy. So it was not clear if the efficiency was better overall. But in this same paper I was mentioning in 2017, we managed to prove that asymptotically for well-chosen parameter, the efficiency converged to something that is very close to logarithm of 2, which is not very far from 0.6. Now, we looked at multiple extensions of these models to try to address different problems. So for example, we looked at the possibility to use associative memories to retrieve data elements when we have just partial information about each subpart. So for example, we do not know exactly what is the value in each part, but we have a subset of candidates and we want to find what is the closest match. Another example is when you want to store data elements of varying dimensions. So we came up with this idea of using directed graphs when we want to store data elements that can have dimensions that sometimes is bigger than the number of neurons in the architecture. We looked at the possibility to use only portions of the neural networks when we want to store pieces of information. And this was useful for applications where we have multimodality. And so sometimes we are addressing only a portion of the data set, sometimes another portion of the data set. And we were also interested in nested systems where we have multiple levels of representation of these associative memories. overall, I would say that the main idea that we wanted to promote during the IRC grant was that there's not just one way to look at the brain, mathematically speaking, or as an algorithm. What happens actually is that when you look at the literature, most models of neural networks consider that it's a mathematical function that takes an input x and produces some output f of x. In theoretical computer science, in semantics, this is what we call denotational semantics. This is just one way of looking at an algorithm, and just by looking at what is the output associated with the input. But there are other ways to look at the semantic of an algorithm, like operational semantics, for example, where we really try to understand what's going on at each operation and how it affects the memory of the system. And I think that what we pushed as an idea during the IRC grant was mostly this vision of the brain where we don't see it as a function to take decision, but mostly as a system that is able to store and reliably maintain information inside the neural network. And this is a fundamental question because it is very surprising that the brain is able to maintain pieces of information for a lifetime, considering the fact that the neurons are very noisy, so we lose neurons all the time. The connection weights are changing all the time as well. So I think it's a very important question to try to understand how we can have reliable memory despite this system that is very susceptible to noise. We were not only interested in fundamental questions, we were also interested in engineering applications of these ideas. And for example, here I have two images, so one on the left, which is extracted from a paper that was written by a master student, Demetrio Ferro. And the main idea of the paper was to show that you can use associative memories to solve the approximate nearest neighbor search problem. So it's an indexing problem, it's an approximate match problem, but contrary to what I presented before, the difficulty here is that you're dealing with continuous vectors. And associative memories are really meant to be able to store discrete vectors. So you have to find a way to map these continuous vectors to discrete versions so that you don't lose too much accuracy overall. And interestingly, there was a very popular method to do that at that time, which is to rely on product quantization. So you divide the vector into subvectors, you quantize them independently. And if you do that, you end up with a structure that is extremely close to the one I presented for the associative memory before, where you have subpart of the network where only one value can be taken. So it was a very good fit for this type of associative memories. On the right, I have an extract of a paper that is a collaboration with University of Tohoku in Japan and McGill. And basically, it uses what I said before. That is to say, the type of associative memories we introduced can be fully binary. So what we tried to do in this paper, we tried to implement a very light search engine that was able to perform requests for a portion of the DBLB database. And we wanted to make use of very promising technology, which are memory stores. In that case, it was magnetitudinal junction technology that they had available at Tohoku, and that can be integrated on top of CMOS. So we came up with this full design where we can basically process requests with very, very little energy consumption. So that brings me to the last part of my highlights. And the last part is really about deep learning. So just to recap, when I'm talking about deep learning, I'm really talking about compositional models that can be represented by graphs. And these graphs basically model the data flow from an input to corresponding outputs. Now, in this graph, the vertices are what we call layers, and the edges can have different meanings depending on where they are located. Sometimes it's just a forward of the information, sometimes it's a summation, sometimes it's a concatenation. What is important is to understand that layers are very simple mathematical functions, which are basically the composition of a nonlinear function h and an affine function wx plus b. So h, most of the time, does not contain any parameter to be trained, and the affine part contains a lot of parameters to be tuned. So this is an example on the left of a very simple search architecture, which is just a line graph. So it's a cascade of operators. It's a composition of the function, mathematically speaking. And on the right, we have a slightly more elaborate model, which is a residual network, where we have multiple flows of information from the input to the output. In general, if you want to reach state of the art, you have very elaborate architectures, which are way more complex than that, where you have really a lot of different ways of flowing the information from the input to the output. What's very important is to understand that during training, what you do is you're going to constrain the system end to end. What I mean by that is that typically you process an element from the input to the output. You compare the output you obtain with an expected output, you compute an error, and you backpropagate the gradient of the error to tune the parameters. To do that, most of the time, people use variants of the stochastic gradient descent. This is important because we know that stochastic gradient descent suffers from catastrophic forgetting. That is to say, it tends to really specialize to the last seen examples. So in a condition where you do incremental learning, you have new classes, new instances, you tend to really specialize to the lastly seen examples and to forget about what you learned before. The last thing I wanted to say about the training is that it's not so easy to know if the architecture is going to perform well in practice. That is to say, if it's going to perform well for previously unseen examples. So to stress this ability, what people are doing often is that they use a validation set. So they cut the training set in two parts: a training set that is used to tune the parameters, and a validation set that is used to stress the ability to generalize to unseen examples. Finally, there are plenty of reasons why they are so popular right now, the deep learning algorithms. I just wanted to cite a theoretical one and an empirical one. So a theoretical one that is often cited is the fact that they are universal approximators. So under normal conditions, you can prove they can approximate any function from a tensor space to a tensor space. But I think that really the main reason why it's so popular is because it's basically the state of the art for so many challenges in machine learning. Now, they are not perfect. And for example, a limitation of deep learning techniques is that they rely on a lot of computations. So they need a lot of memory to store the parameters. So they consume a lot of energy. So they are not so well suited for example, real-time applications or for embedded devices. So there are multiple ways to try to limit this complexity of the systems. And one example of a contribution we had this year, it's a collaboration with the University of Toronto, was to work on quantizing the weights and activations. So what we wanted to do is we wanted to let the training procedure find the best number of bits for each value in the network instead of designing it ourselves. The problem is that the quantization is a discrete phenomenon. It's not differentiable in nature. So we came up with this very simple interpolation between different quantization steps, and we made the learning procedure decide how many bits it wants for each parameter. Now you see here some results that were obtained on ImageNet, so it's considered to be quite a competitive benchmark. And you see in blue and red the curves corresponding to the accuracy of the baseline where you don't have quantization, and in blue the method we propose. So you can see that eventually they reach the same performance. But as you can see, the average bit length in the proposed method is quite low. It's below 4 bits. So it's quite good results considering the complexity of the task. Another example on how to limit the complexity of a system is to use pruning. So when you use pruning during training, you try to identify portions of the network that are not so useful to the decision, and you get rid of them. There are many ways to do that. Some ways are easily exploitable in practice. Other ways are more hard to exploit in hardware. But we came with this new idea last year. So it's a paper by Roti where the idea is the following. So we worked on convolutional layers, and we had the constraint that for each slice of a convolutional layer, we wanted to keep only one non-zero weight. So the reason why we try to do that is because if you do that, ultimately, you can re-express the convolution as the composition of a multiplication and a spatial shift of the input. And this is very interesting because it's much lighter to implement on some hardware designs. So not only you benefit from the fact that you reduce the number of parameters thanks to the pruning, but also you can really leverage in terms of computations because you get rid of the convolution in the end. So I didn't want to add too many examples, but I would like also to mention that we were also interested in distillation techniques, where we have typically a teacher architecture that contains a lot of parameters that is used to supervise the training of a small architecture that's called the student. And we came up with this idea of trying to use graph signal processing to represent the geometry of latent spaces and to distillate this geometry from the teacher to the student. So we managed to obtain quite interesting results with this idea in the papers that we submitted this year. Another line of work on which we've been very interested is the question of generalizing convolutional neural networks to slightly irregular domains. So we were particularly interested in that topic during the PhD of Jean-Charles. And the first problem we looked at is a problem where we have sensor networks, and these sensors have GPS coordinates. They are irregularly spread in space, and we would like to somehow exploit the underlying structure when we're going to train a deep learning framework. So at that time, we were interested in very naive approaches where basically we use an approximate convolution using the underlying metric space to define the weight sharing scheme in the deep learning architecture. A few years later, we came up with a full methodology that is maybe more principled, where we used graphs to represent the underlying structure. So the methodology really consists in first inferring a graph if you don't have a graph, then using the translations I introduced before to translate the graph signals on the graph. And once you have the translations, you can define the weight sharing scheme for the convolution. You can perform data augmentation, which is very important in practice for regular signals. And you can also design coarsening and the weight sharing of upstream layers. So interestingly, in that paper we submitted in 2018, we were able to show that when we apply this methodology to very regular signals like images, for example, we are competitive in results with regular convolutional neural networks. So it's interesting because I don't think there are so many methods in literature that are able to compete in this specific case. Now, of course, this is not so useful because when you have images, you can use regular CNN, but still it was interesting to show that you can have a true extension of it using only the graph structure. Other highlights I wanted to mention are different contributions that happened in the past few years about trying to promote tools to better understand, visualize, and manipulate the training of deep neural network architectures. So an example here is an extract of a paper by Miriam she published last year, where we wanted to promote an objective loss for training classifiers that is not the cross entropy. So the reason why we wanted to get rid of the cross entropy was there are multiple reasons, but one of them is usually when you use cross entropy, you have targets that are defined for each class in space. And these targets are chosen completely independently of the initial distribution of your parameters and your data set. So if you look at an architecture that you train, at the beginning, your points are randomly spread in the output domain, but you don't build on that. You just completely disregard that. You just force the points to match specific regions that you pre-decided. And we believe at that time that this might be problematic, in particular when you are facing noise in the input, so for robustness, but also for transfer, because you have this kind of very sharp transitions during the learning process. So we came up with this other idea of using graphs to try to build on top of the initial configuration. So instead of expressing targets as absolute positioning in space, we look at relative distance between the points, and we try to make sure that they are well separated in the output layer. But as you can see on the top row here, we kind of do not change that much the density of points in different portions of the space. We've been also very interested in the notion of robustness. So for example, Carlos during his PhD worked on proposing solutions to improve robustness of trained architectures. But I wanted here to mention another work that is very recent. So it's a work by a master student, Théo Giraudon, from this year, where he promoted this idea of maybe the evaluation of robustness that consists of averaging radius of robustness of different samples is not so good. So many people, when they want to evaluate the robustness of a classifier, what they do is they look at all samples in the data set. They look at how much noise they can add to these samples without changing the decision, and they do an average. But the thing is that sometimes you have samples that are harder to robustify than others. If you consider, for example, a classification scenario, you have class domains. If you sample a point very close to the boundary, you cannot expect to have a large radius of robustness for this point. So it's going to bias your overall estimation of robustness. So we came up with what we call this difficulty-aware notion of robustness, where we try to take into account this distance to the class boundary when we compute the actual average radius of robustness. A last point I wanted to mention with respect to these tools is work we did in 2018, where we looked at the possibility of using graph signal processing to monitor the training of deep neural networks. So we came up with this kind of observations where you see during the training how evolving the specialization of each layer. Interestingly, in the paper, we came up with this idea that maybe we could use these tools to predict the overfitting or let's say the generalization ability of the architecture in the end. And based on this idea, we contributed to challenges this year at NeurIPS, which is a predicting generalization deep learning challenge, where you have to guess the generalization ability of a train architecture without a validation set. And we ranked third, thanks to this technique, which is quite good considering the size of the lab. Other contributions I wanted to mention are related to few shots, few label, and incremental learning. And for example, Eugene, who is a new PhD student, worked this year on the idea of using graphs in the context of few label learning. So you imagine that you have a lot of data, but only few samples are labeled, and you would like to make good generalization out of it. The problem is that you cannot use a huge deep neural network to train because, of course, they contain tons of parameters. You cannot tune all these parameters with just so little information. So most of the time, you rely on a transfer procedure where you use a pre-trained feature extractor, and then you build on top of these features. And what we came up with is this idea of trying to connect different samples. So some of them are labeled, some others are not, and to exchange information between these features. So basically to kind of run a low pass filter so that we remove some noise from the representations before we go to prediction stage. And interestingly, so this paper managed to rank first on the very classical benchmark of the field, which is the mini ImageNet benchmark. And Eugene had a new contribution a few months after, and he still ranked first on this benchmark. In terms of incremental learning, so as I said before, the problem of relying on the stochastic random descent is that it suffers from catastrophic forgetting. So a lot of people are interested in trying to see how you can learn in conditions where you have streaming data and you have new classes, new instances that are coming over time. And in 2018, we came up with this very simple design of a solution where we tried to exploit to the maximum the specificity of feature vectors. And namely, we observed that in feature vectors, so since feature vectors normally are trained for a different task, they act sometimes as an adversarial noise to your case because they have been trained to separate things that you don't care about in the new task. So we decided to split those feature vectors into sub-vectors in order to try to mitigate the effect of this adversarial noise as much as possible and to perform individual decisions about the process and then the majority vote. So as you can see with the examples I've extracted from the paper here, so this is examples that were run on Cypher 100, I think. And as you can see, we were able to outperform most of the method at that time. Interestingly, using a very similar idea, this year I have a student, so Quentin Jodelet, who is now a PhD student with Tokyo Tech, who came up with a contribution to the 2020 CVPR challenge on continual learning. It's the track that is called New Instance and Classes. This is the most difficult one, and we were able to rank first on this specific challenge. So, of course, all what I presented is thanks to a lot of collaborators, and I could not cite all of them. And I wanted to highlight specifically international collaborators because I feel like in my work, I benefited a lot from my interdisciplinary research, from the fact that I spoke with mathematicians, with electronicians, with people that are specialized in hardware design, in signal processing, computer science. And it's very interesting to have this kind of confrontation between different points of views. But it's even more beneficial, in my opinion, when it's with people that have different backgrounds in terms of they've been to school in different countries. My feeling is that when I speak with French collaborators, often we have the same point of view, the same approach to the problem. But when I speak with people that were raised in different countries, I'm often very interested by the fact that we have completely different approaches about the same problem. So I think I was a bit long on that part. I have roughly 5 minutes left to talk about future work on directions. So of course, the problem that I found to be very enthusiastic is the problem of few label and few shot learning. In particular, there's a question that is extremely interesting, which is a question of trying to come with universal features for any subsequent problem. And I think that everything that is performed right now using self-supervision is very promising, like using the same features to solve different types of supervised problems, really robustify the features for other tasks as well. And I found that extremely interesting. And I think that combining that with the ideas I presented before with graph smoothness and different laws that are not really targeting this specific problem on which they are learned could be very beneficial. In terms of few label, I think a very interesting problem would be to use active learning, where instead of choosing at random the samples to label, it would be very beneficial to try to select the samples based on the density or based on some other priors we have about the distribution. And ultimately, I find it very interesting the fact that if we have universal extractors that can solve any separation of our points into classes, the question mostly becomes a combinatorial question, where we want to identify uniquely a set based on some samples from the set. There's a huge literature on the domain coming from, for example, associative memories, but other domain as well. And I think it would be nice to try to make a mix of these approaches. Another very interesting problem, I think, is a problem of trying to perform deep learning on edge. And I'm not just talking about doing the inference close to the sensor, which is, of course, a very interesting problem. But I think the most interesting problem is you want to adapt the training procedure to new data that is acquired close to the sensor. But this is not just a problem of hardware. This is also a problem of incremental learning, because of course you cannot control how the data is acquired. You cannot store all the data sets. It's also a problem of self-supervised learning, because you cannot expect to have an expert to supervise your data close to the sensor. And it's also a problem that you don't have a cross-validation set, so you cannot basically use a validation set to know if you're performing well or not. So you need theoretical guarantees about the fact that your method is going to perform well in practice, or at least that is going to have some behaviors where you know that it won't change the decision for a small change in the input. And I think a very promising candidate for this engineering problem would be to try to mix deep neural networks for the ability to extract features that are universal somehow, and associative memories for their one-shot provable performance. And I really think that this is a promising direction of research for this problem. Finally, in terms of future work and direction, I've wrote a few pages in the manuscript on what I consider to be really the main problem of the field today, which is really the tendency to go to benchmarking, where we identify very limited settings, very limited problems, and we work on this very limited problem. And often we look at so limiting problems that we forget that if we were facing the same problem in practice for a real application, we would do it completely differently. In particular, I think it doesn't make sense to say that we have to perform well on a domain starting from scratch. Most of the time when we are facing real problems, we can use tons of data that is available online to pre-train, to transfer. And I think this is very important, of course, when we want to have good performance for this kind of competitions. And I think that one problem is that when people are talking, for example, about transfer in the literature, they really think of this one-time transfer where you learn features on a huge data set to be transferred one time to a problem where you have less diversity of data, for example. But in practice, when humans learn, it's not the way it works. I think it's more like a sustainable transfer where you solve multiple tasks. They are mutually beneficial. And it's not like it's one time you stop training this and then you use for that. It's more like they can enrich each other over time. If we want to do that, we really have to understand how we can update the weights of layers in these architectures without questioning their ability to solve the problems for which they were trained before. And I think it's a very interesting question of research about trying to understand in the layer updates, the portion of space where we can make changes without questioning this behavior. And finally, I think the main question is to extract this kind of features that are universal again, but not only universal, that are combinatorial. It would be much simpler if we could come with representations that are extremely sparse, where instead of thinking of them as vectors in directions of space, we think of them as subsets on which we can do union intersections and all these things that people have been doing in AI for a long time. And I think that all these different approaches could benefit from graph signal processing, for example, for the updates, from associative memories for this way to combine elements together and to understand how we can make these different operations, but also from deep learning itself for its ability to generate these reusable features. So I think it's a very promising and exciting direction of research where I could really benefit from my past experiences. So I'm a bit over the time, so I'll be very quick on this summary slide. So it's just a slide that is meant to stay here for the discussion. There are some points in the last block that I didn't have time to address because I wanted to focus on scientific content, but I wanted to say that I'm very interested in questions related to ethics and AI, popularization of science. Every time I had the opportunity, I tried to promote science to the general public. I've been very active with the organization of contests and competitions, and as you can see also, we participated to many contests in the past, and I think it's a fun way to do research, and it's a fun way also to focalize on a specific problem. And also, I'm very concerned about trying to to educate more, and I think the perfect way to do that is to rely on online courses and MOOCs. And I didn't have time to mention that. I just wanted to say a few lines. Thank you very much for listening to me, and I'm ready for your questions.
Thank you, Vincent. Thank you for your presentation, which was very nice and very clear. But we're now going to ask questions, and the first to ask questions are traditionally the reviewers who reviewed your manuscript. It's traditionally we also begin by the reviewer, the furthest from the defense location. It's a bit more difficult today to decide where is the actual defense location. But anyway, since you are located in Brest, I'm suggesting that we begin with the questions of Pascal Frossard from EPFL.
Okay, thank you, Rémi. Thanks, Vincent, for the nice presentation. I think it's a very nice overview of the numerous contributions you have put together, and quite a few inspiring ideas for future research. So I'm especially impressed by the breadth of your high quality work. So that's very good. Congratulations for that. I have a few questions. Maybe I will not ask them all now, so that I could come back later and leave space for questions for the other jury members. So my first question is probably on the translation, the translations that you described in the GSP part of your work. There are different ways to define translations. There have been different ways. There is your way. There is people who have worked through convolutions to define the translations. Now people are also looking from the angle of optimal transport type of ideas to define also that. Something similar to translation. What is your take on that? What is a good definition of translations for signal on irregular structures?
So I thought about that for a long time, and I would say right now my feeling is that there's no one answer that is perfect for every possible application or domain. When it comes to very regular structures, or let's say slightly irregular structures, I think that what we came up with is a nice extension. But it really doesn't have any meaning when it comes to very abstract graph structures like with hubs and small world architectures, social nets. I think other approaches that are more generic, that could be deployed for any types of architecture, have this interest of being applicable to many domains. But then they often have this problematic of not really matching what you would expect for regular domains. So I know that there's many work, you cited optimal transport. I know that Antonio also was involved, or with Benjamin Giraud. Other people proposed alternative definitions as well, with different priors in mind about what the translation should be. My feeling is that there's no one answer to the problem. I would say it really depends on how we want to leverage and exploit these translations that we defined. And depending on that, we might want different specificities. For the case of this specific work I was talking about, we were really interested in anisotropy. So we wanted really to have this notion of translating to the right, to the left. And this is why we came up with this completely different notion of translation from the literature. But of course, again, if you go to a social net, it doesn't have any meaning. You cannot have this kind of thing. So the short answer for me is, I don't think there's like one perfect answer. I think it really depends on the problem. And I think the problem is still very open today. Like, I'm not convinced that there's one definition that is granted to be the best for a specific domain of application. So actually, I mentioned that I have 4 PhD students that did not define yet. Raphael, who just started 1 month ago, he's going to delve into that as well, because again, I think it's a very promising question of research.
Okay. Thanks for this response. Could you go to slides? Well, your numbering of slides is not easy, so I guess 9. you have many things per slide. So I wanted to talk about a bit about the brain signal processing applications that you described. Yes, this one exactly. So I think that's indeed a popular field of application for GSP. Could you describe a bit more what was the task you considered here, and how did you actually solve it? I think you were a bit fast for me on this one.
Yeah, sure. So it was more of a proof of concept. So we decided to use a very standard data set from the field, which is a Haxback data set, where, if I remember correctly, the way that it's acquired is that so you have these people that are watching at images on the screen. You have the fMRI scan at the same time. And really, you have all this data where you have the fMRI scan, you have the category of the images, and there are different ways of creating a data set from that. In the case of this study, we did a binary classification problem where we wanted to distinguish two categories. So there's a difficult task and an easy task. And it's not so convincing in terms of the application, I would say, because Haxby is probably kind of a toy data set. It's not, there are many other data sets that are more recent and that are more challenging to work with. But it was really just to showcase that, as you said, I mean, probably neuroimaging is a fantastic sandbox for everything that we are doing in graph signal processing, because it sounds like the graph structure, if you take a functional graph, can be very abstract and very complicated. And at the same time, there are real applications behind, and the field of neuroimaging is evolving more and more towards using network neuroscience and graph-based methods. So I wouldn't say that this experiment was so convincing in the end. It was more like really just to showcase that we could do that. The methods we use are not the ones that people will use for the community now to obtain the best possible performance. Probably the way we infer the graph structure could change as well, could be updated with recent literature. But still, it was interesting to show that. Sorry, I have an echo of myself. So it was interesting to show that for this specific study, we still can benefit from this very specific framework and from the construction of the graph and the sampling of the signal in the graph. So, for example, right now, Miriam is looking at a slightly different problem where it's also brain decoding, but it's not visual imaging, it's different. So we try, for example, to identify subjects' age or things like that. And we also use graph signal processing. And again, it shows quite interesting performance. And I think one of the reasons is if you construct the graph correctly, there are reasons to think that the signals you observe are more informative in the high frequency domains, because the low frequency is really based about some background tasks that have nothing with what you're looking for exactly for the specific task you're working with. And the experiments we made recently showed that if we only keep the high frequency on the graphs, we can improve the performance of the systems quite well, even on these new data sets. So again, I think there are plenty of things to look at in that direction. It's very promising and very exciting because it's probably one of the best possible application fit for our GSP in general.
Yeah, I agree. It's quite fascinating as an area in general, at least for me. Okay, cool. Thanks for this response. And maybe a last question for now. I cannot resist of asking a question about the robustness part. So if you could go to slide 13, I think, when you represented the work of yes, exactly, this work. So I didn't get it completely if you were addressing the problem in terms of robustness to random noise or robustness to adversarial noise, which is also typically studied. I didn't get that part exactly, and I didn't get exactly how you solve the problem actually at the end. Okay, so in the paper we were really interested in the worst case scenario, so adversarial noise, and really the point was if you have an embedding that is low dimensional, it's very likely that you will have points that are very close to the boundary and points that are very far away from the boundary. I mean the actual ground truth boundary, not the boundary of the classifier. And what we wanted to show is that depending on how you sample your data set, you may actually be biased by the difficult examples that you sample. Like, for example, we did experiments with SciFar where we sampled the hardest examples, and hardest are measured by the loss at the end of the training. And
easiest examples. And we measured the average radius of robustness based on these different samples, so the hardest and the easiest ones. And interestingly, when you look at that, it's very non-robust in the sense that it gives very volatile decisions depending on the classifier you use. So if you run the same classifier multiple times, you will have large variations in the estimation of your robustness. But if you try to take into account this difficulty, that is to say, if you weight during your averaging of the radius of robustness, the importance of each sample based on the loss you obtain during training, which is a proxy to the difficulty of this example, you can make this process of evaluating the radius of robustness, the average radius of robustness more robust to retraining the classifier, changing the samples. So really the purpose of the paper is to say it might not be a good measure to just average over all samples as if they were all equal. We should take into account the fact that some of them are difficult, and we should be aware of that, because if we are not aware of that, we could give too much importance to this kind of non-typical examples.
And then did you move to the next step? Then that would be then using these ideas to make the classifier more robust also.
So I would love to. So Theo was I said he was a master student. It was a mistake. Actually, he was in M1, so he has not finished yet. So I hope that he will come back for a PhD and we can continue this work together. But the paper was submitted very recently. Actually, it was submitted to ICASP, so it was like 1 month ago. So it's very early work, but for sure I'm passionate about this problem. We tried to publish a couple of papers in the past few years, including Antonio, who is part of the jury, about this problem of robustness. I think it's a major question of the field, and I know that you're very active and in the question. So it's a very important question. And again, here we were not so concerned about a methodology to improve robustness, but really about trying to understand if we measure the things correctly or not.
Got it. Okay. Thank you very much. I'll stop here for now.
Thank you,
Mr. President. Thank you. You're muted, I think, Remy.
Thank you. Sophie Achard can ask the next questions. Sophie.
Yeah, thanks. Yeah. Can you hear me correctly?
Yeah.
Okay, nice. So first, thanks, Vincent, for inviting me participating in this jury. I really liked reading your manuscript. It's very impressive amount of work in this very competitive field. And I would like to stress also the fact that you are in all your manuscript and in your presentation, we could see that you are really doing long-term research, in the sense that the citations are referring to different periods of your research career. It's really nice that you can follow all these fields all along your career. And your presentation was really clear and, of course, fast, because you had lots of things to say, but it was really nice. And I will ask you some questions first on the graphs. So you spoke about graph inference, and can you comment on so you spoke essentially on the graph inference for using graph signal processing, but there are many other techniques. Can you comment compare these techniques to this one, and what's your feeling about that?
Okay. Thank you for the comments, and thank you for the question. It's a tough question because, of course, the plenty of domains of research have been interested in this question of finding graphs from observations, even way before graph signal processing emerged as a field.
Yeah.
And a lot of techniques have been proposed with different priors, different ideas in mind, different ways to leverage the graph structure afterwards. It's a very problematic question, I would say, that often the problems on which we try to retrieve a graph structure, we don't have a ground truth. So basically in many domains, and I think in neuroimaging it's the case often that people use these techniques. They find a graph structure, but then they interpret this graph structure. They say, okay, oh, it has some meaning with respect to this or that. But it's very qualitative. It's not quantitative. So it's very difficult to come with kind of a unified benchmark to know what is a good method to infer graph from signals. So of course, we've been very interested in the question. In some aspects, the paper from Mathilde, where we have these different ways to infer the graph structure, was aiming at comparing different techniques. But more generally, we tried, for example, in collaboration with Gonzalo Mateos from University of Rochester, to come with this possibility to create very diversified benchmarks to emphasize the interest and the drawbacks of different methods with respect to the type of signals and the type of methods we want to apply once we have inferred the graph structure. But when we try to design this diverse set of problems, we always found that we were too restrictive on the types of usage for these graphs. And that makes everything very complicated. I think it's a fundamental problem for sure. There are so many domains where you have these observations and you know there's some underlying structure and you would like to have an access to an explicit such structure. But to me, it's really not clear what a good solution is. If you don't tell me how you're going to use the graph afterwards, either to have some qualitative statements or either to be one ingredient of a downstream procedure or something. For example, when you first tried to infer graphs for different problems, so we gathered different approaches, so graph lasso, thresholding the covariance matrix, or different estimations of the covariance matrices, priors based on the graph signal processing framework like Smoothness, and ultimately we found that most of the graphs we obtained were very similar in shape. Like if you look at the difference in terms of the Frobenius norm or the edges of the graph between the different methods, it's relatively small compared to what it could be. So somehow I found it interesting that despite they have different priors about the relation between the graphs and the signals, it ends up producing graphs that are kind of very similar. So my feeling is that there's something kind of universal hidden behind that I cannot have an explicit, I cannot name right now. But my feeling is that there's kind of a minimum that you expect to retrieve in terms of edges, in terms of correspondence between vertices, whatever the technique you're going to use, considering a set of signals. And making this correspondence in terms of how the different methods work, what are their priors, what is the algorithm, what is the optimization procedure, could be very hard to do, but I really think that there's something interesting to look at here. For example, I was very surprised to see that for the CIFAR dataset, I mentioned that we made some experiments. So CIFAR, it's natural images. So for natural images, you expect that pixels that are adjacent are going to have very similar observations. And a natural graph that you expect to be a good representation of such signals are grid graphs, because of course they have this underlying 2D structure. And actually, I was very surprised to see that if you take the whole CIFAR dataset, which is reasonably big, so you have like, I think 50,000 samples, and these graphs contains 1,024 nodes. And if you look at the different graph inference methods, they almost all finish by finding something that is extremely similar to a grid, like it's almost a grid. And yeah, there's something that should explain why all these methods are so connected in the end. I know that there's been some reviews recently, so two of them, so one from EPFL and the other one from Penn and collaborators, and where they tried to come with this overview of all the methods. But I really think that what is missing is this kind of fundamental link between every method we come up with. There's something that seems to be always there, and I would like to understand how if we could design a method to find this kind of robust graph structure.
Yeah, thanks. Yeah, I like your answer. And in terms of robustness, but on the graph, what do you have any ideas about the impact of the misidentification of edges for the use of the graph afterwards?
Yeah, this is a passionate problem of research as well. So there's been recent works that have been very interested in studying, in the specific case of graph neural networks, the robustness of their method with respect to changes in the graph structure. And it's wonderful to see that in terms of graphs, it can be quickly dramatic. Like if some edges are lost in the process, it completely changes the graph structure, it completely changes the decision, because one edge can have so much importance into the overall structure. It's very interesting as a problem. The issue I have with, I would like to contribute to this field of research, to be honest. But the problem is that right now, I'm not completely convinced of the interest of graph neural networks as a whole. I'm not so sure that they demonstrated their superiority to other methods, like very clearly on an actual real problem. And because of that, I don't go there yet. I think there's still work to do on the methods themselves before questioning the impact of the graph structure. Right now, I don't know if the impact of the graph structure to the overall method is because of the graph neural networks that were implemented, that maybe are not that robust themselves to changes in the graph structure, or because of the graph inference process, if you see what I mean.
Nice. I may ask a more general question on the biological inspiration. You did not speak a lot on this in your presentation, but in the manuscript, you said in particular that it is fair to say that modern artificial neural networks show little similarities with their biological counterpart. Can you comment on this? What's your perspective about that?
Okay, I have to be careful because Julie is in the jury, and she was the head of General Biocomp, and I think that neuromorphism, like neuromimetism, is a very interesting perspective of research for long term, and I admire people that try to draw bridges between something that we know so little about, which is the brain and how it works, and technology and electronics, and it's really a very, very nice ambition. At the same time, I think that quite clearly in the field of deep learning, when the models were introduced, the vocabulary was mostly about coming from what we think we thought we know about the brain functioning. So we were talking about the visual cortex, about the bottom-up, the top-down phenomenon, about a lot of things that were coming from the what we already knew in neuroscience at that time. But I feel like for the past few years, there's been a drift where now people have less the tendency to try to make references to this literature. So for example, the term deep neural network is more and more the term deep learning. And you see that by avoiding the term neuron, I think it's fair to do that, because when you look at the deep neural network architecture, it's fair to say that there's very little similarity with what we know about the brain today. I mean, there are so many different types of neurons. The organization is so complex. It's very, very different from what it is in terms of technology. But when they were introduced, I think they were introduced at a time where it was a fair model, mathematical model of what we knew at that time about the functioning of the brain. So for historical reason, I understand that. But I think that today there's kind of a huge gap between what we do in terms of engineering, deep learning, the way it works, the way it's trained, everything about deep learning mostly is so far away from what we know from the brain, from the new discoveries about the brain functioning, etc. There are some very strong people, much better than I am, much more famous, that say that deep learning is neuro-inspired, bio-inspired. So I have to say it's just my feeling about that. But my feeling is that there's no evidence that these models are good candidates to model the brain. And maybe that's good. Maybe that's not what we want to do. What we want to do is to have good accuracy, good performance for engineering systems. So there's no reason to think that by chance the solution we're going to obtain that is good for these specific applications happen to be exactly the way the brain works. But still, I want to say that I still find very interesting the domain of research that tries to bridge these two domains of research, because of course there's still a lot of problems that we cannot solve today, and drawing inspiration from something that works is always a good idea, I guess, even if we don't know exactly how the brain works.
Yeah, nice, thanks. And I will finish with a question on the ethical aspects of AI. So you put a short paragraph in your manuscript, but I want to know, in terms of perspectives, if you had the possibility to do something, to contact the political people, to do something from the scientific point of view, what do you push? So you said about open science and so on, but I think it's not sufficient. What sort of other things would you have in mind?
I think, like everyone in the jury and most people in the audience, we share the threat of what's happening today in the world with the rise of dogmatism and questioning of science, and I feel guilty because I have access. I know what science is. I guess I have an access to part of science. I know how it works, and I feel like it is our duty to educate people, to share this knowledge with the general public, and to help them understand what it is exactly. And my feeling is that it's really related to this question about ethics. Like, for example, there is a big threat today of the misuse of the technology we are working on, like AI. We see what's happening in China, for example, with the social points, etc. We see what's happening with big American companies, with manipulation of the opinion of people, which is not necessarily desired, but which happens in practice. And I think that the best way to avoid terrible issues with this kind of technology is to really educate the people, to make them aware of what are the dangers, and to help them have a critical point of view about the technology that is an educated critical point of view, not just a dogmatic point of view, like I reject because I don't like people that are in the system, or I don't know what, but really understanding what are the strategic questions that they should think of, and they should act as a citizen in their vote, in their elections, to try to make things right. And I said I felt guilty because I think it's a problem of the job. I mean, when you're in the job, you're used to communicating with scientists all the time, and sometimes I feel like we don't realize that our language is inaccessible to non-scientists. Like we don't have the same way of expressing ourselves about political problems, about results in general. It's very rare to see a scientist say, "I'm sure that it is true that," or if he says that, maybe he's not a scientist. And I think we should really explain that. We should really spend more time speaking with non-scientists, explaining what we know, why we know what we know, and how they can help, how they can intervene. And right now I have the feeling that, at least in France, there's kind of a huge gap between scientists and people that don't understand what science is and that reject science because they feel like science is rejecting their beliefs. And that's kind of, to me, one thing where I would like to if I had the opportunity to talk with let's say a representative of people, I think I would tell them that. I would tell them we have to communicate better between the medias, the scientists, and the general public, so that they don't believe that we are narrow-minded people that are only focused on their career, and they understand that we try to build a truth, a knowledge that is beneficial to everyone. And to me, that's really something I wish I could do something more about that, but I feel like I have very little hands to act on that. But
yeah, that's the problem. Thanks. I'm very happy with your answers, and I will leave the other member of the jury to ask their questions. Thanks, Rémi.
Thank you, Sophie. And I will now leave the floor to Julie Grelier for the next set of questions.
Okay, thank you very much, Rémi. And thank you, Vincent, for the invitation to be in the jury, and very nice presentation. As I said in my report, I'm very impressed by all of your results, and yeah, how interdisciplinary your research is, and how you are able to make very important contributions in each field. So I have a few questions, quite practical questions, actually. So yeah, if you come back to your work on associative memories, you know, on slide 11, where you showed that you could improve on Hopfield and Wilshire models. It's unclear to me if now with these improvements, these systems are now ready for, you know, real world applications. I mean, what would you say now that you have worked on this? Would you say that what you proposed is enough, and does it make sense to really make that in hardware for, you know, for applications?
Thank you, Julie, for the comments. Thank you for the very tough question as well. It's a hard question to answer. The problem with associative memories is that, contrary to, for example, to machine learning problems, you say, okay, I have to solve this problem. I have no solution. So how I do it? And you come with a solution, so you solve the problem. Associative memories, when you look at the problem, you have very naive, simple solutions to the problem. Like if you have a collection of data elements, you want to find the closest match, you can compute the distance to all the elements, order the distances, and you find the closest match. So it's more a question of making that more efficient in practice, like reducing the complexity without having too much impact on the accuracy of the system. So for sure, it's not a domain where I expect that there can be like the same kind of impact as in deep learning, where we are really solving problems we did not know how to solve before. But on the other hand, there are 2 points I think that are important. So the first one is in terms of really just what we can do today with these systems. I think it still would make sense if you identify really let's say the hardware problem for which you could benefit from reducing the complexity. I know that in the past we've been discussing a lot with the collaborators on using this kind of technology for CAMs in caches, and I think that it's one domain where we might find like a set of parameters, a set of constraints for which this solution would be slightly better than existing ones. But it would not be like a huge gain, like divide by 10, or I don't know what the complexity. It would be maybe small gains to be expected, like a small reduction in the area or the consumption. The other aspect is, I think fundamentally speaking, it's interesting to consider that what we consider to be an asset for technology, which is these memories we have these hard drives where we can store lots of memory. It's reliable. We can retrieve memory, and we built a full domain of computer science on top of these very reliable devices. But maybe this is not so good when it comes to cognition and to trying to make interesting things emerge from a system, to have this type of perfect memory that is not at all what happens with biological systems. And my feeling is that the research that is performed in the field of associative memory might have the interest of showing that it is difficult sometimes to differentiate certain types of information, and other types of information tend to naturally create attractors that are far away in the dynamical space. And that might be something that could be an asset when it comes to trying to come with systems that are able to automatically create like associations between different elements, like non-supervised learning, for example, or the use of this kind of technology for neuromimetic systems, where you try to have a representation of the cognition that is maybe more inspired by what we know is happening in the actual brain. So in short, I would say there is no clear killer app right now. Like this associative memory is the way to go for this app. I still am convinced that for some specific applications, it would perform better than existing alternatives if you find the good parameters, if you're on the good regime. But I really think that the potential of it is more in having a different view on how we store and manipulate data elements when we conceive an AI system. And I think there's a lot to do in that direction, like trying to exploit this ability to self-organize in the information instead of having this perfect memory where basically nothing is happening because each vector is just a vector separate from the other.
Right, right. So yeah, so that was my next question actually. So it means that you, and this is what you said in your presentation also, that you find them more interesting to be linked to a deep network, for example.
Yeah.
Right. And so
yeah,
how you see, how do they connect? I mean, how do you? Sorry, I go to the.
No, it's a fair question. For example, very recently, like last week, we submitted a book chapter on that specific subject on trying to transform deep learning architectures into deep associative memories. And the idea is it's always the same. I mean, associative memories are discrete in nature, so they cannot be trained with differentiable algorithms. But there are two solutions. Either you make sure that your deep learning architecture is going to produce at some stage representations that is discrete, which is possible to do. There are tons of ways to do that in practice. Or you use smoothing techniques during the optimization process where you progressively transform your problem that is differentiable into a problem that is basically discrete based. So there's a lot of techniques in that area as well, where you start with associative memories, for example, that would be continuous, where you have continuous operations on the vectors, continuous representations in each subpart. And during the learning, you push more and more the representations to become binary. So this is what we came up with as a strategy in the book chapter I was referring to, where at the end of the learning process, we basically have exactly the same operators that I described here, where you have these multiplications that everything becomes discrete in the end, despite the fact that all the training was differentiable. And the interest of that is it's much easier in the end to understand what's happening because all the operations are much simpler. It's also easier to implement in hardware because, of course, you don't have to do multiplications anymore. You don't have to rely on that. So there are multiple ideas on how to do that.
Okay, but it means that you don't see the deep network and the associative memory as two distinct modules.
Well, you could do that, but if you do that, it comes a bit like the idea presented about the work by Demetrio, where basically what you have to do is to map the continuous representations to discrete representations. And often when you do that, you are very suboptimal because you optimize your two systems independently. So
yes. So there is no way to train something end to end. You mean?
Exactly. What we're doing right now is we're trying to push for this method where we're doing the both of them at the same time. And the solution we found is to embed associative memories into a continuous domain and to make them differentiable and to push along the training process them to become more and more discrete up to the point at the end of the training process where they become fully discrete.
Okay.
And I think it's important really to have this end-to-end design if we want to reach competitive performance for engineering applications. I mean, for example, compared to deep learning. So for the chapter I was mentioning, for example, we show that we can achieve exactly the same accuracy as a deep neural network itself. So it's not a simple deep neural network. It's like an elaborate one. It's a residual network with with a lot of optimization on it. And at the end, it's just that we transformed it into a succession of associative memories layers, and we reduced the number of multiplications by a fair amount. And we still have exactly the same accuracy. And we did not go that far, but my feeling is that we probably have almost the same boundaries for the class. So we have a very, very similar semantics of the architecture, despite the fact the operators are completely different. And to me, that's a promising also direction of research, where deep learning would be used to tune, to parameterize, but at the end, we will use the mechanism of associative memories because they are lightweight, because they are efficient to implement, and because it's easier to understand the decisions that are taken by the architecture.
Yes, okay. So you can make them more explainable.
Explainable and robust. I think robustness is really a key question for us. And when things are discrete, it becomes easier because basically robustness becomes just looking at when you're going to. So if I take the example of a deep learning architecture, it's basically just a linear piece function. So you separate the space into linear parts, and you have boundaries. And when you transform that into the deep associative memory, you just basically make it a constant piecewise function. So it really becomes understanding how far away you are from the transition from one piecewise piece to another one. And I think it's a nice way of looking at the problem because at least from analytical point of view, it's much easier to understand exactly what's happening and why we lose robustness.
Okay. So you basically apply them exactly to the same problems as deep networks.
Yeah.
So that's stuff you need to make them competitive.
It's maybe the lack of imagination, or maybe because I've contributed so much lately to more machine learning, and I've been used to this benchmarking. But I really feel like if we want to have some impact, if we want to convince people of the interest, we have to obtain good results on their problems, and not to come with our own problems on which we show that it might be interesting. So the first step for me is to show that we can really bring something to the table on what people are doing right now, and then maybe open directions of research to other problems.
Okay, thanks. And I have another question. Yes, so basically for hardware, well, and in the general case, we know that as you say, stochastic gradient descent is maybe not the most efficient way to train your network. And in your manuscript, you mentioned to use randomness. So, well, my question is very tough, but yeah, what would you replace stochastic gradient descent with, basically? Because we want to keep the accuracy, right? So, what can be as good in terms of accuracy, or slightly lower, but much more efficient? It's complicated.
So for example, imagine that you want to train a deep learning network which weights are binary. So one way to do that would be to use a surrogate of the gradient to try to learn weights that are actually continuous, make them almost binarize at some point.
Yeah.
And if you do that, you can achieve very good performance in the end. Another way would be to use like replicated simulated annealing or this kind of techniques, where you randomly sample weights and you just flip them, and you look at the energy function. And if the energy is decreasing, then there's a probability that you accept the change indefinitely. If the energy is increasing, then you refuse the change. What we showed in a very recent contribution with mathematician colleagues is that typically we reach the same accuracy on some data sets when we use these two methods. The only difference is the time it takes. Well, it's a big difference, right? But the ending result is about the same. The accuracy is about the same. Now it takes way more time for the random algorithm to reach the good configuration. What I'm thinking is that that's true when you use GPUs and computers. But maybe if you come up with a hardware design that is extremely efficient for processing binary weights and you want to train it on chip, then maybe for this kind of cases, it would make sense to train the network by doing this kind of random flipping of bits, looking at how the energy evolves on your data set, accepting or rejecting the flip and continuing like that. could be more lightweight than actually computing the backpropagation of the gradient on really weighted values, that what you need for the alternative.
Yeah, because it takes more time. It's more. You were not referring to the time on the GPU, right? You were talking.
Yeah, exactly. I was referring to the number of iterations.
Yes.
So the number of iterations is like in the worst case, you can prove it to be exponentially larger. But let's say that in practice, it's not that bad. For example, for training MNIST, okay, I'm not proud of it. MNIST is not like very fancy, but it's still MNIST. And MNIST, it took about 2,000 steps on an architecture that was using convolutional layers to train and reach an accuracy that is state of the art. If you compare with standard procedures, it's maybe 10 times more than what is required. So if you imagine that you come with a hardware implementation that is more than 10 times cheaper or faster to process the feed-forward to look at what is the effect of the flip, then basically you have gains in overall in energy consumption or training time.
Okay, but you don't think it increases in complexity with a more complex problem?
The problem would be then to test, because since we don't have access to this hardware right now, we have to rely on GPUs, which are not specially optimized for this kind of processing, or at least it would take some time to engineeringly do something very efficient with this kind of architectures to see what happens with more challenging data sets. But I was unable to run simulations for now with more complex data sets because it takes too much time to train.
And it's difficult to have a mathematical estimation of the number of iterations.
We have a mathematical expression, but it's like an upper bound that is extremely loose. And so if you look at the upper bound, you say, okay, there's no feature to this. But I don't believe that. I believe that really, if you give me a very decent binary implementation of a very complex architecture trained on ImageNet, we could maybe train it with bit flipping, with specific techniques that have been introduced lately for training this specific architecture's binary efficiently, if it's fast enough for the forward pass. And for this type of architecture, actually, maybe there's no alternative solution to train on chip. Like if you have a lot of layers, if you want to compute the backpropagation, you have to keep in memory the activation of each layer when you do the backprop. You have to update the weights. It's really a lot of computations, a lot of memory, and I'm not so sure that you can actually do that with very limited hardware.
I agree, but there are some algorithms like proposed by Yoshua Benjo.
Equilibrium propagation, for example. Yeah, there are alternatives. And I think equilibrium propagation is very close to what I was describing actually in the philosophy.
Okay.
It's really trying to replace the stochastic gradient descent on an objective function by an energy that you try to minimize. And that has basically the same.
You see it that way, I see. Yeah, it was another question I had, because in your manuscript you mentioned doing some random perturbations to the network. And to me it sounds very much like ECPROP when you nudge the output.
Yeah. It's extremely similar. Actually, the reason why I'm not mentioning explicitly equilibrium propagation is because we based our work mostly on recent work by Amari and co-authors. That is, I think, very similar in the idea, but that is in a different community and that was published a bit before.
Okay.
So we mostly base our approach on their paper, and that's just for that. And we were targeting really this community. But you're right. I mean, it's very similar to equilibrium propagation, at least in the formulation. And there are some implementation of equilibrium propagation that are probably doing very similar things to replicated simulated annealing.
Okay. I think my time is up. So thank you very much again.
Thank you.
Thank you, Julie. So we'll continue with questions from the examiners. And there's no doubt that Antonio is the furthest away. So Antonio, the floor is yours.
All right. Thank you. Thank you so much, Vincent, for the very nice presentation. I also enjoyed reading your manuscript, and I enjoyed reading about all the research. Of course, I'm familiar with some of your work, and I have to say that it was a pleasure. It's been a pleasure to work with you and with your students. And it's kind of amazing what you can do with, you know, a short visit and some brainstorming, and how it kind of expands into lots of different things. And I learned a lot from that, and you know, I really appreciate your work. So I have a few questions. The first one, kind of going back to what Pascal was asking about the shift operation. So I wanted to mention this work. So I wanted to mention, you know, in your example, in your document, you talk about the grid graphs and the torus graphs, you know, and I think one of the issues in examples like these where you're in 2D is that in the graph representation forgets that you're in 2D, right? And you know, we know that the image is in 2D. We know what up is and what down is and what left and right are, but the graph maps all of this to a 1D frequency definition. And there's the work by Saito at UC Davis that has explored some ideas related to this point on, you know, and at least explain why this is problematic. And I was wondering if there is a way forward where maybe we find a different way of defining frequency, where we take into account the fact that the data is really in a Euclidean space, the points are in Euclidean space. And it's not just a matter of measuring the distance, but maybe also keeping track of, you know, how this distance behaves in different directions. I don't know if you have any thoughts on this direction.
So thinking about the problem, I'm not so sure that the problem is well posed. Like, imagine I give you a random geometric graph, and you forget about the positioning of vertices. And now the question I'm asking you is, can you retrieve the main directions in space? I'm not so sure that you can always do it, and probably do it. So my feeling is that it might be too complicated of a problem to actually retrieve translations based only on the edge matrix. My feeling is that maybe instead of proposing like alternative definitions of the frequencies or the graph Fourier transform, or maybe it could be that, but it would be nice to incorporate additional information, for example, from signals on the graphs. For example, when you think about a classification problem, you use convolutional layers because you want this equivariance to translation. You want the translation to the input to be a translation in the output. And I think that if you have enough data, you could use this data to actually understand what are the invariances that you could exploit from this data. And that could help in designing the translation on the graph structure. Like maybe express the problem of finding the translation not just as taking as input a graph structure, but taking as input both a graph structure and a set of signals. And for example, if you consider the Cypher 10 problem, again, you have these 10 classes. You could try to say, okay, I know that within these classes, there should be some invariant transforms. And maybe I can use this huge amount of information to try to guess how they are obtained. So I would say to me that's a promising direction of research, like changing the nature of the problem, exploiting additional information when we want to find our translations. What you said was perfectly right. I completely agree with you. If we have a grid graph, the problem becomes a toy problem, and it's not so interesting anymore. But my main issue is that if it's not a grid graph, I don't know if there's any evidence that we can find something that is better than what we have already today. Like, I'm not so sure that we have enough information for doing better than just projecting a 1D translation to this graph structure that can be of a very high intrinsic dimension.
Yeah, so I agree that the problem is difficult, you know, if you go away from the grid graph, and I just wonder if there is a way, you know, for example, such as the grid graph, to have a slight modifications of the definition that allows to capture directionality. I think it's a challenge. I think it maybe, we don't. I mean, if you just rely on data as an example, you may have a way of replicating some of these invariances, but it may give you a very complex, complicated function in the graph frequency domain, for example. So yeah, you can always recreate it, but it doesn't have lots of insights when you consider it in the graph domain. So
one thing that is interesting that I should mention with respect to your question, I think it's related to it, is when we started this work with Sebastian about having this vertex domain definition of translations, our aim was actually to show the opposite, to show that it's not possible to retrieve directions if we lose the embedding of vertices in the 2D space, if we only have the graph structure. And we were very surprised that we could actually retrieve this the directionality from the neighborhood properties of the graph. It was not something we expected to obtain at first. And this was a mind changer because, of course, this was a negative of what we were expecting to obtain. But still, I don't know how to answer the question properly. I don't know if a graph is enough. I don't know if we need to use extra information. And I don't know exactly what is a translation for a non-grid graph. So I don't know how to evaluate whether we're doing something good or not. So.
Yeah, I was not expecting an answer. I was just, I don't think anybody has the answer to that question. It's just, kind of a brainstorming or discussion idea. Also related to Bastien's work. So in this this work on the uncertainty principles, so you make a point, and you have this figure that you had in your papers, and you put it in your document about this graph where there's an edge weight that is epsilon, and two edge weights that are fixed. And I mean, you make the point that there's a lack of continuity, but I think there's a lack of continuity if you don't consider the fact that for every epsilon, you would change the shortest path, right? So if you're looking at if you're always considering the shortest path, then that's not discontinuous, right? I mean, there's going to be an epsilon that is non-zero, for which you switch from the direct path of weight, epsilon to the other one, right? And so I guess my point looking at that work is that I mean, this is an interesting point in practice. In most of the work you see in this area assumes that the graph is fixed, so you don't have edges going to zero. And of course, if you introduce this idea of a shortest path, things are non-linear and kind of complicated. But I mean, it's not. I wouldn't call it a discontinuity. I would just say that as some edges become smaller, the shortest path becomes different, and that's not that easy to treat mathematically. So it's more of a comment than a question, I guess.
I think I agree with your point completely. I think when we wrote the paper, the main concern was we didn't understand why they chose the geodesic distance in the initial paper. We thought that there are more robust choices for estimating a distance between vertices in graphs. And we wanted to point out that the choice of the geodesic distance is problematic because it's only well defined for a tropical algebra. So if the non-existence of an edge corresponds to an infinity distance between the corresponding elements. And often we find it convenient to kind of disregard these points when we write about graph signal processing. We kind of suppose that everything is well defined, and we have this kind of assumption that zero corresponds to the non-existence of an edge, despite the fact that zero should correspond to merging the edges. And I think this is what we wanted to argument about, more this point, that geodesic distance is probably not a good choice for graph signal processing because it was not meant to be defined for the classical linear algebra.
Okay. Yeah. So moving to the last part of your presentation. So one question I had. So in some of the work we did together and some of the work you've done after that. So graphs are used to understand the training and how so the features are learned in a way that allows you to separate classes, for example. And one comment that I've had from people in machine learning is that they say that at very high dimensions, these distances become unreliable because of the curse of dimensionality. Yet, you gave an example where in this recent NeurIPS competition, a method based on these ideas did very well. So do you have a sense of why is it possible to be robust to very high dimensions? Is it because of the way things are learned, and therefore the intrinsic dimensions are not as high? Just wanted to hear your thoughts on this.
So it's really just intuition speaking, but it's fun because in a deep learning architecture, typically what happens is that the deeper you go in the layers, the more dimensions you have, and the highest the dimension of the space become. And at the same time, the more you become aligned with solving the task. So what I believe is that there's kind of a trade-off between, like, if you take just random weights and if you look at the latent species, I'm pretty sure that the cost of dimensionality will be dramatic to all the estimations we make, and we end up with things that are just not exploitable. But since we constrain the end to be mapping to very low dimensional spaces, actually, my feeling is that the more we go to high space dimension, and the more we are constrained about the task. So there's kind of a double phenomenon, like we increase the size. So yes, the cost of dimensionality is more of a problem, but we could become more and more a manifold on which we try to separate the items. So basically the distance is still meaningful thanks to that. So it is my intuition about why we have that. Also, through the experiments we perform, we often look at latent spaces, but we really focus on these last ones, like the last one, the penultimate one, the few before. And I think it's also for the same reason, because they really have this intrinsic dimension that is reduced because of the tasks they are solving, compared to the first layers that are maybe more like random embeddings of features in larger spaces where there's more space to find the separations. But as I said, it's just an intuition. Now, I agree with you that it's problematic because, of course, the graph construction depends entirely on it. But at the same time, thanks to your collaboration and to the work of Carlos and Miriam, we have now quite a few publications where we show that we can actually have positive results still by using a very naive estimation of the distance and constructing these graphs. So I really think that the argument is not strongly motivated. Like as soon as we have good results, there's a reason for it, and the metric makes sense for sure. Otherwise, we would not have good results. So.
Right. Thank you. So let me ask you the last question. And I mean, my questions are a little bit open-ended, but this one is really open-ended. So I enjoyed your your last slides about things that maybe should be done in the context of AI machine learning to get away from these very narrow problems that many of us tend to work on, of having a data set with a task that is well defined, and then trying to beat the competition, right? And 1% better, or 0.5, and so on. So this clearly resonates with me for sure, and I think with a lot of people. And this idea that that there's a way of extracting, maintaining some reliance on data sets to make decisions, but extracting something more fundamental that goes across tasks, for example. So I think it's a really interesting idea. I guess my question here is, can we do this by just relying on data? So, if we still only use data and data validation, can we really hope to do this, or are we just going towards even more complicated problems where instead of, you know, a single data set validation, we need to do a multi-data set validation. But, you know, we're sort of playing the same game with more complicated rules, and we need more GPU hours and, you know, more of everything else. But, you know, we're still solving kind of this other problem, right? I mean, is there any hope to do any of this just with data?
That inspires me for two points. The first one is that I'm very admirative of the work of Joshua Tenenbaum on precisely trying to explain how humans are using a lot of priors about the world to learn, in particular about the physics of the world, and that could be also things that could condition a lot the type of object we recognize. Like we have kind of a very natural assumption about the signals in general, which is the coherence of the object we want to recognize. Like they are connected in space. It's very rare that you have to identify an object in the real world that is made of two independent parts that are far away from each other. These kind of assumptions are very strong, I guess, in the human cognition, and helps a lot in self-supervising, in creating robust features from unannotated data. But at the same time, I want to say that before I switched to machine learning, I was always very curious about how people come with benchmark. Like someone said, okay, we have 10 classes, we have 5,000 examples per class, and this is the data set, it's called Cypher10. Now let's try to solve it. How did they know that one day we would be able to reach 100% accuracy? And it is a question that I've been asking myself for a long time. And at the beginning, I was even wondering if whether it was possible. I was like, okay, maybe the limit is 93% and you cannot go above. And actually, when you do 0.5% more, it's way better than what existed before. And now the last results on Cypher10 are like 1% error rate. And I'm so so I don't understand why, but it seems that some people have faith in the fact that you can extract a lot of things from data, and they were right about it. And I wonder what is the limit of all that. So in terms of what we're discussing about, like going beyond just solving a task, but maybe trying to understand what is the machinery that has produced the input, what are the hidden variables, what are the independent causes for all that. Maybe it's intractable, maybe it's not possible to solve it. But I've been converted to this religion of machine learning, and I feel like maybe it's possible. And it's worth at least trying to do it, trying to see how far we can go with only data. And I'm always impressed of what we managed to do so far, because I feel like that if you ask me the question 5 or 10 years before, if you ask me, is it possible to go to that precision, to that accuracy with that data, probably I would have said no. I don't think so. So yeah, it was an open question. It's an open answer, but my open answer is I really am impressed with the domain, and I think I don't know. I can't figure out what the limit of the current technology and the methodology is. And because of that, it is allowed to imagine that you can go further and you can find this kind of causal variables in data. But I have no strong argument to say it's possible. And maybe you're right. Maybe we need additional data. Maybe we need priors about this data, about the world we are living in if we want to go further. Or maybe these priors limit us from finding solutions to other problems. I don't know. But yeah, it's really a very passionate question.
Right. I mean, it's hard to say, but I would say that like many other things that we see in technology, a lot of this comes from, Moore's law. And so, Moore's law gives us more memory, more computation, but also it makes it easier to create data sets. And so, we have, sets of data sets that increase by the day. And, there's, not to minimize the effort involved in creating a data set when it, collecting data or maybe recording data with sensors and so on. But it's much easier now than it was 20 years ago. And now when we look at all these data sets and what we learn from each of them, I think there's something narrow that you can see in each of them, but there may be something that goes beyond that, where you need to use multiple of these. But in any case, they should be, you know, in my opinion, curated better, right? I mean, whoever came up with Cypher 10, great, but you know, now the data set itself takes a life of its own. Everybody uses it, and we forget how that was, you know, what choices were made. So we need, I think, a little bit more science in, you know, selecting the data sets.
I completely agree. I want to cite Carlos. So I remember when having a discussion with Carlos at some point where we were discussing about how to present deep learning to people, and I came with this argument that I presented in the slide that it's universal approximators. So that's a good thing. And he answered to me, no, that's a bad thing. And I was like, why? And he told me, okay, basically you're saying that every bad generalization of data you can approximate. Mm-hmm. And to me, yeah, that's kind of mysterious a bit why it works so well. Why is this specific technology? I think that we are focusing on deep learning because it's very adapted to the hardware, basically. It's very efficient to compute. We can backpropagate efficiently. And this is the main, to me, it is the main reason why we are focusing on this model. But imagine that we had hardware that is more efficient for processing, like, I don't know, order 2 multiplication of matrices instead of just simple matrix products. Maybe we would have a different parallel universe where deep learning is about these specific operations. And but yeah, there's something I cannot grasp today about the limit of what we can do, about why the data sets are enough or not enough, and how people come with data sets, and how they think that this data set makes sense. For ImageNet is the same problem. Like ImageNet, when they introduced ImageNet, what made them believe that one day we could have a good performance on that? What made them believe that we could compare the performance of a computer trained on just 1 million images to a human being that have observed, I don't know how many different scenes during his whole life, and so impressive that in the end it works. Yeah, it's a very interesting problem that I don't know how to put science, let's say, analytical words on it. Right now, it's more like a discussion that is more philosophical than scientific about that. But I think it's really the core of the problem of machine learning, trying to understand why it works, and would it work if it were a different universe, if it were different rules about creating the data, and what makes it work for the specific data sets.
Right. Thank you very much for all your answers. That's all for me.
Thank you, Antonio.
Thank you. So we'll continue with the questions of Sébastien Lefebvre.
Okay, so thanks, Rémi. So thanks also, Vincent, for this invitation. So I was very pleased to join the jury. And okay, even if I was not a reviewer of the thesis, I was really appreciating the quality of the manuscript and the quality of the talk. So it has a very strong tutorial quality, and I was impressed by the very wide pool of contribution, and it has already been said by the previous member of the jury. So the issue I have with being very far from the first member who was talking, that I have many of my questions that were already asked, and I was very satisfied with your answer. So I will probably not ask you again about how to actually use the associate memories in terms of real problem. I think you answer quite well, because we were quite doubtful on the applicability of these methods when we were using them in Romain PhD, and so I understood your answer, and I was also happy to actually see how you were highlighting the links between the three parts, the three components, I would say, of your research, at least as they were presented in the manuscript. Okay, so still I found a few questions to ask you, and maybe they won't be too technical, because you had a lot of technical questions before. But yeah, basically, okay, I will start with maybe a provocative question. So in your work, everything is related to the graphs. But so you know that in the deep learning communities are okay. It is very active community, both in terms of research and engineering. So many people are working with deep networks. What would you say to convince someone to use graph when doing deep networks, or when I will say doing AI in general? And is it a requirement? So should AI go through graphs?
So thank you, Sebastian, for the comments, and thank you for the provocative question. I'm not sure I'm the good advocate for graphs, despite the fact that I contributed to many papers using graphs. My feeling is that this is what research is about. Like, we don't necessarily know in advance whether what we're doing is going to be like the solution, the main solution to be retained afterwards. But I really believe in diversity of approaches. There are really key core questions in deep learning right now that we should answer if we want to really make the technology usable in many practical settings. We talked about robustness, we talked about few shot, we talked about generalization to other domains. There are many other questions as well. And my feeling is that these questions are extremely important. Like, they could really be a game changer for society in the coming years if they are solved. And I think a good approach to this problem is to try different paths. And this is what I mean by diversity. Graphs are kind of ubiquitous. You find them everywhere. They are very natural candidates for representing a set of data and the relationship between these data elements. Now there's quite an elaborate literature on the subject, including in machine learning before deep learning, but outside of machine learning as well. So I would say it's a promising direction of research in the sense that we have a lot of experience with this methodology, and it makes a lot of sense to try to use them to, for example, represent the latent spaces, or to represent the structure of inputs for deep learning applications. So I'm not saying that this eventually will stay and remain as like the major improvement to deep learning of 2020, or I don't know. But I say it's definitely today, up by the standards we have and the vision we have on the field, a very promising possible solution. There are others, but this one makes sense. And this is the reason why I wanted to explore it, because I love graphs. I mean, I was born with graphs, I would say. I've always been around graphs. So it's something that I really enjoy because of the genericity of the method, the very strong, fundamental, discrete mathematical results you have on graphs. And at the same time, all this linear algebra that comes to graphs. It's a fantastic toy for mathematicians, where you have all these different approaches that merge with the same formalism. And using them for deep learning, I would say at least it has the advantage of giving a new vision, a new explanation, a new exploration of what's happening inside deep learning. So maybe in the end, we will just realize that it was not enough, or it was not the correct paradigm for looking at this. But I would say today, we don't know. We don't know yet if it's the good direction or not. So it's worth exploring, because we are researchers, and because, of course, if we knew in advance, we would not be doing research.
Okay, thanks. You look very convinced and enthusiastic. So yeah, it's very nice to see that. So maybe still on this point. So so since you are on the slide on compositional AI, so one of the direction of future work you had identified, could you just re-explain or explain what would be the added value of graphs to address these challenges? I mean, I understood what you already say about the structuration somehow of the latent spaces, and you were already saying a few words when you had the question on explainability. So you already said a few words on that. But okay, here typically, so the graph is hidden probably everywhere. So in a few words, so typically for, let's say, for transfer learning, so how you see the importance of graphs?
So I guess I always had the idea that when you want to understand what the function is doing, you have two choices. Either you look at the function itself and its mechanisms, which in deep learning would mean you look at the weights and you try to understand how they are shaped or they are constrained, what they do. Or you can look at what's happening between the input and the output. So you look in terms of the transforms that the function is applying to the data set. The problem with deep learning, as I said, is that despite they are compositional, most of the time the representation you obtain at a specific layer is not constrained directly, explicitly. The constraint comes from the descent of the gradient from the output. Because of that, it's very hard to treat examples individually. Like if I give you the representation of one image at a given layer and at the output of the following layer, you don't have much to say about it. Like there's no information in it. But now if I give you a batch of inputs, a batch of representation at the input of the layer and the corresponding batch at the output, you have much more information about the transforms that have been operated by this layer to the geometry of the space. And I think it's very important to understand that in this intermediate representation, absolute positioning is completely meaningless because of the type of operations we use. The last layer, most of the time, is just a linear separation. So it's just interested basically in the linear separability of the data. But if you rotate the data, it doesn't change anything. It works as well. And so what is more informative is really the relative positioning of data points in these intermediate spaces. So that's the reason why very quickly you come to graphs, because graphs are really a natural way, again, to express this kind of relationship between all the data points. So it's a natural way, I would say, to try to express what this geometry looks like at a specific layer. Now you chose the example of transfer, and I think it's a very good example. With transfer, what's interesting is when you train the backbone architecture, the architecture that is generic and that is meant to be used in different tasks afterwards. At the same time, you're very interested in leveraging the information from the task, and at the same time, you're very non-interested in the very specificities of this task. And I think that in terms of for example, the cross-entropy we were mentioning before, what the cross-entropy is doing at the end is that it's really mapping the specific classes of the task to specific points in space. And the reason why people take the penultimate layer is because precisely they consider that this last layer is completely meaningless when it comes to a new task, because it's over-specialized to the specific data set. But the reason why they choose a penultimate layer is not clear. And actually, there's been a lot of studies where they show that it's not necessarily the best option. Sometimes it's better to use a combination of different representations or another representation before in the architecture. When you pose a problem in terms of a graph function, it's different, because the graph is not interested, again, in this absolute positioning of space, of points into space. It's really interested in seeing the connection that you have between the points together. And with respect to classification, you're interested particularly in how close are points that belong to distinct classes. So it's a bit like, for example, there's been a lot of literature on the use of the triplet loss for face recognition, for example. When you have this type of data sets where you want to generalize to a lot of new data, it makes more sense to think of the classification problem as a problem where you want to act on the relative distances between items of the same class and items of different classes. Then it makes sense to actually map these items to a specific point in the target function. So I think that the philosophy that's behind the ideas I'm defending in the manuscript of using graphs for solving these problems, to me, it's very natural. Again, the steps are, first, you understand that absolute positioning is meaningless. Then you say, I'm interested in relative positioning. Then you say graphs are a very natural way to model this kind of relative positioning. So why not use graphs?
Okay. Yeah, it's very clear. Indeed. Okay. I will move a little bit away from graph, but not that much. Actually, come back to the work you've done on associative memories. So I understood what the link you were establishing between associative memories and deep networks. And if I understood well, you end with the fact that at the end you want to solve a problem rather with an associative memory than a deep network because it is more efficient. But then in the same time, you presented associative memories as a tool that allows to do either exact or approximate matching. So does it mean that we could reformulate every problem to be solved as a problem of matching?
That's a fantastic question. It's a question that I asked myself for several years after my PhD. A bit the same as machine learning, actually. Machine learning, I was really wondering if there's a limit to what we can solve as what we cannot express using the formalism of machine learning and what we can express. And the same for associative memories. I was really concerned, is there an example of a problem that I cannot solve by just explaining some associations between items I obtained before? And actually, I kind of convinced myself that the expressivity of the approximate match problem is huge, in the sense that if you take denotational semantics, so imagine that what you want to do is you want to approximate a function using an algorithm. Using associative memories, if you have infinite memory, you can basically store all the combinations of inputs and outputs. So that's kind of avoiding a bit the point of the question by answering like that. But my point is, obviously, there should be minimum amount of memory that you can achieve to have a fair approximation of your function by choosing the correct pairs of input outputs. And my feeling is that if you look at the problem this way, every problem you can solve with, let's say, machine learning typical methodologies, you can solve with associative memories for about the same reasons. If you sample the space enough, then you can guarantee that you will have a fair approximation to your function. But again, it's kind of an abstract answer to your question, in the sense that when you train machine learning algorithm, you generalize. And this is really what you're looking for, having good performance outside of your examples. When you're training associative memories, it's the exact opposite. You're really only concerned about what's happening in the vicinity of what you stored in the memory. So these are kind of two dual approaches, sometimes contradictory, yet the two approaches have the same goal of trying to implement a specific function. It's just that the way you're going to train them is different. For the associative memory, it's a storing procedure, so you're really interested in reproducing what you learned. And for machine learning, it's really a generalization, so you're interested in interpolating and extrapolating what you learned. But yeah, the short answer is, I don't see why you could come up with, let's say, an actual engineering problem that I could not solve with associative memories. If you can express the problem as just a function that takes input and processes outputs, I can always express that as an associative memory matching problem, an hetero-associative memory problem, where I try to find the input that is the closest to your probe, and I find the associated outputs.
Okay. So, but maybe not so. Okay. Maybe with a network that is so large that it cannot really handle the task. Anyway. Okay. Maybe a question that is maybe further from actual scientific questions, and maybe a broader question, given the fact that you have now spent more than 10 years as a researcher in the field, and so you probably and we saw actually during the presentation that you built your own opinion on the field, and so I would like to understand maybe why actually. Okay, let me reformulate like that. So the amount of contribution is very significant, amazing, I would say, and there are, I think, very strong contribution in machine learning as well. And despite this, I was a little bit surprised that actually you don't end with a stack of NeurIPS or ICLAR or ICML papers, or even working on an image dataset. So maybe you could have many papers in computer vision top conferences. And I think your work deserves it, definitely. So what I see instead is numerous archive submissions. And I was wondering, is it, so I assume that maybe you tried and you were not successful. So if this is actually what happens, do you have an explanation about this? So is actually your line of research not, do you think it is not in line with the current direction of the community? What do you think of that?
I think it's a very fair question. And of course, you're right. I mean, we tried for NeurIPS, for CVPR, for iClear. We have a couple of submissions that we tried to push, and ultimately they did not get accepted. And sometimes it was a bit difficult because the results of the reviewers were quite positive, but still it was not accepted in the end. To explain why is for me difficult, because if I knew, of course, I would have more papers in these conferences. I've came up with multiple explanations over time. I spent quite a lot of time discussing with Hervé Jégou, that you know. And I remember that he told me that I publish way too much and I should publish less and focus more on specific contributions. And it's an advice that he gave me once, and I remember we discussed a few years after, and he told me again the same thing. He told me, again, I've checked your publication list, and you should publish less. You should spend more time on the papers if you want them to get accepted. So that's one explanation I have, which is that I should spend more time on making the submission strong enough for publication and really go further into the experimental parts, into the design before submitting. Now, the reason why I don't do it is because I feel a bit trapped by how things work. And let me just elaborate a bit on that, because I think it's an important question. I started mostly with contribution in information theory, signal processing, computer science. The rules are completely different. I would say that if you come with something that is solid from the theoretical background, and if you are convincing enough that it could be applied to an application case, it's often enough to convince the reviewers that what you do is interesting. And most of the time, I have the feeling that when you submit a paper to one of these venues, people take reviews as a way to strengthen your paper. So they really have the positive feedback of trying to help you in making the paper better for the next time. Now, when I switched to machine learning, and for the first attempts, I was very surprised with the reviews I received. Like sometimes the reviews were extremely short, and they were only like saying, okay, yeah, this is an interesting idea, but I'm not convinced. So it's marginally below the acceptance threshold. And it was frustrating because we had no idea what was missing, and we had no idea on how to make the paper stronger for the next submission. So I think we lost a bit of time when I switched to machine learning, because basically we didn't have the experience of why it was marginally below the acceptance threshold. Now, after my visit to Milan, things have changed a bit, because now I think I have a better vision of what's happening in the field of computer vision in particular, and machine learning more generally, and what is expected for the publication to go through. And I have a more, let's say, a negative opinion on the papers I published before, and now I can better understand why they did not meet the threshold that people were waiting for. But it took me quite a while. And the last submissions we had, for example, this year, some of them, so we have a paper at CVPR, a paper at NeurIPS that is accepted. And we are going to have, I guess, maybe, maybe I won't try it, but we are in the process of reviewing with another conference where we have good results as well, which is a top conference in the domain. So my feeling is that it's happening now. And the reason why it didn't happen before is because I was missing some keys about what was exactly expected. And I have to say also that there's a problem for me. So you said sometimes I give my opinion, and I have an opinion to give about that. It's a bit difficult because in France, as you know, the students, they have a 3 years PhD. And of course, some of them, when you hire them as a PhD student, they tell you, okay, my ambition is to become an academic. And we know that the competition is hard. We know that if they want to obtain an academic position, they need to publish. They need to have enough papers to convince that they did different things, that they had an impact, etc. So it's very risky in my situation to try to target just one major conference with such a student, because I have the feeling that if the paper is rejected, then the risk is that when the student is going to defend, he's going to have a profile that is going to be below some other students that maybe targeted less selective conferences, but have more publications in general. So it was a bit difficult for me to find a good trade-off between both. Now I have a well-rounded strategy for trying to solve this issue, but it really took me a few years to come with a solution.
Okay, thanks. Maybe a last question, if I may. And so also related to the fact that you spent more than a decade of research work on these different topics. Now with your experience, if you were back 10 years earlier, would you make some different choices in terms of the primary topics you should focus on? Maybe because some of the topics you were studying were not a posteriori were not that interesting or not that effective, or I don't know. What's your feeling after 10 years?
I'm very sorry, but I don't know how to answer that, because if I could go back 10 years in the past, I would publish a paper about residual networks, a paper about batch norms, and I would be the most famous scientist in the world right now. But being in 10 years in the past with the knowledge I had in the past, I don't know if I would make things differently. You know, it's I've always felt like research is really a conjunction of many things. I talked about diversity before, and I think that it's always worth exploring paths. Some of them are going to be meaningful. Some others are going to be not so effective in the long run. But when I see, for example, what happened with deep learning and the winter of AI and people that completely disregarded the field for a long time, I'm so happy that these few people continued and believed in what they thought was the correct answer. And I think that this perseverance is really important in science in general. And for that, it's a bit related to the question about graphs. It's not because we don't have results that are like extraordinary today using graphs in deep learning that we want in 5 years from now. And I really believe that we need people that are free to make choices to continue in that direction. There's not that many people that are free. When you see in machine learning, many people work for companies. Some of them are free. We know some of them are very free, but some others are not that much. And I think it's also a duty. I mean, it's a responsibility to have this freedom and to explore these possibilities that others want. Because maybe there's something very interesting behind. So you had this provocative question about associative memories and graphs, and so even today I can't answer. Is it something very promising or not? I still don't know. What I know is that at the time I worked on that subject, it looked promising to me, and that's the reason why I wanted to pursue this work.
Okay, no, perfect. I think there is no good answer, and I think it's perfectly fine to have to analyze the research as you do. Perfect. Yeah, and I agree with you basically. Okay, thanks very much for your question, and
thank you.
Give back the floor to the chair of the jury. Thanks, Remy, and thanks, Vincent.
Thank you. So we're about to conclude this question session, but before we conclude it, I would like to ask also a few questions. I think I will limit myself to 2 questions. One slightly technical. It's about the catastrophic forgetting problem that you mentioned at several occasions, which, if I understand well, is somehow the fact related to the fact that algorithms to train networks have a limited and local view and limited memory. So how would you connect? Can you envision connecting this with various forms of longer-term memorization of in a learning process?
So it's really a central. Could you cut the mic, please? Yeah, sorry. So there are many people that are interested in the question. It's a very active field of research, and it has been for a very long time. There have been multiple solutions for that. So, like, for example, freezing some connections so that they remain the same for multiple epochs. So they have kind of a souvenir of what's happened in the past. You have methods that use neurogenesis. So basically, the idea is to say that when you learn new tasks, when you have new data, you incorporate more material to account for this new task, so that hopefully it will use different passes in the gradient descent that will not destroy everything that existed before. You also have methods that works on pseudo memory and rehearsal, where you try to capture some, let's say, footprints about what the data looked like before, so that you can regenerate this kind of data afterwards. This is, for example, something that is very used in reinforcement learning. And so there are plenty of ways to try to make something last for long during the training process, even using the stochastic gradient descent. Quentin, so the student I talked about that is now a PhD student in Tokyo Tech, his subject is precisely that, incremental learning. And he did this very nice review recently where he tried to see where the field is trending and what is working for actual problems. And we were very surprised to see that basically almost always the best solutions are based on memory, like actual external memory. So it seems that the best solution up to date to tackle this problem is to actually find a way to remember things that occurred in the past and to put them artificially in the batch of newly processed data, so that we still take them into account into the training procedure. I think one thing that is very interesting, again, is this kind of duality between learning and storing. Like, if you look at machine learning, you have approaches where you aim at generalizing, like with deep neural networks, for example, but you have also solutions that are based on memory, like nearest neighbor search, for example. And usually these methods that are based on memory, they don't suffer from catastrophic forgetting precisely because they don't have this kind of training procedure. It's a one-shot learning, where basically you have to increase the size of your model every time you have new data that is coming. And I think that somehow finding again ways to connect learning, storing, and maybe finding storing as an explicit thing that we want the network to do would be maybe another line of solutions for this kind of problems. For example, in the past in the lab, so I was not involved in that work, but I found it very interesting. Some people tried to train neural networks with double objectives. So one was the cross-entropy loss for classification, for example, and the other one was really meant to reproduce past examples that were trained with the network. And I think that it's very interesting to try to, because we know that there's some memory in the parameters, for sure. There's been plenty of works where they show that you can reconstruct some inputs based only on the weights, or at least some statistical properties of the inputs. So there is some form of memory. And trying to explicit this memory, especially for this purpose of avoiding the catastrophic forgetting, is something that I found very interesting. Also because somehow it connects to the idea we have in mind of why humans do not suffer from catastrophic forgetting, and from this ability we have of spontaneously remembering like pieces of events and things to memorize them better in the long run.
Thank you. And okay, maybe a last question. You mentioned your concern about ethical aspects of AI in general. you already gave some of your viewpoint on the outreach, the way the scientists could work on the outreach to for the awareness of the general public. But do you also envision scientific problems? I mean, feeding your scientific research by defining or identifying specific problems that have an ethical nature and could have could benefit from scientific insights in your field.
Yeah, sure. I mean, when we speak about ethics and AI, many people think about the biases of the training sets and how they are going to affect the train architectures. I think it goes beyond that. It goes also to the fact that we always have a moral point of view on data, that we do not feed the network. For example, there's been this accident a few years ago where I think it was Google who, sorry, I think the mic is echoing again. Thank you. So I think it was Google who made this this labeling of an image of a monkey as a Black American. And the thing is that you can see it as a bias, but here I don't think it's a bias. It's more related to the fact that there's a proximity in the feature space between what identifies Black people and what identifies a monkey. And trying to find a way to avoid that can only happen if somehow we color the data we give with some specific notions of what we want to avoid or what we want to separate, what is allowed and what is not allowed. And I think it's a very tough question because ultimately the complexity of data is able to incorporate sometimes biases that are obvious to the human eye in a way that is very difficult to leverage. I have an example in mind. I don't remember where I read it, to be honest, but the example is interesting anyway. It was about an insurance company that was trying to predict the price of the insurance. And without a surprise, very quickly, an optimal system was taking the decision based on the sex, the gender of the user. And so they wanted to get rid of it. And they just suppressed the input. And they obtained about the same results. And by looking at the internal features, they discovered that basically the network is trying to infer if it's a male or a female to take its decision. And that's something that I found extremely interesting because I feel like there's all these discussions about the biases of data sets. And my feeling is that it's not just that. It's not just biases in the data sets. It's really more about what we want to forbid in terms of separation, segregation, and what we want to favor in terms of putting together. And in my opinion, there's plenty of things to do in that direction in trying to understand how it can affect the learning procedure, again, without having too much impact on accuracy, because when we regularize a neural network, we know that often it comes with a price. And I would like also to delve into these questions. So I have to say that we are going to start a PhD next year with a private company that is an insurance company. And these are kind of the questions that we are going to address as well, because there's some rules, like European rules about how you take decisions to decide the price for a user, and you cannot do whatever you want, and you have to somehow be convincing enough that you did not take the decision for bad reasons. So these are fantastic questions to explore. The question of the relations between the decision taken by an automated system that is only trained to perform as good as possible on a training objective, and what, as a society, we consider to be acceptable as a solution or not. So I don't know if your question was referring specifically to this question, but I think it's a very important question that is more technical, that is really more about how to train without having some specific properties that we do not want to appear in the training procedure. I think that also when, in terms of technical aspects of AI, there is another question. So I don't know if your question was related to that, but a point that to me is fundamental which is the popularization of the technique to small labs, to small companies. And I think that today, the fact that most people are working on data sets that are provided ultimately by Google, Facebook, or big companies is very problematic in the long run, because we provide methodologies, we put the code online, the code is available to everyone, so in particular it's available for these companies, and they only have access to the data. And so I've always found that quite weird that we are focusing on these benchmarks that are basically company benchmarks that nobody else could really make use of because nobody else has the data. And I think it should raise more questions about how we conduct research in the field. And it should also raise questions about how the solutions we come with are going to be beneficial to other people than these very big companies.
Okay, thank you. I promised I would only ask 2 questions. So I'll keep my promise, but I'll just congratulate you again because both the manuscript and the defense were really, well, both impressive in terms of your contributions and in terms of clarity. I think that the jury will now convene in a separate Visio meeting, and I'm assuming that we'll be back on this Zoom meeting when we are ready after our discussions.
Okay, thank you.
Thank you, and see you soon.
Ça y est, on est de retour.
Rebonjour Vincent.
Bonjour.
Ouais, ça va, on n'a pas été trop long?
Je suis pas du tout stressé.
C'est bien.
Je ne sais pas combien de temps on a mis, mais on t'a fait patienter un peu. Okay, I'll continue in English, of course. So I don't see everybody, so I'm not sure. I would like to be sure that all the jury is back in the Zoom meeting.
We don't see you.
I think everybody is here.
Okay, you don't see me. Okay,
Yeah.
It will be better with the camera.
Yeah.
And Vincent, as you can see, I put the headphones on because it seemed that there was some echo during the defense. So I think we are all here. Vincent, on behalf of the jury, I would like to congratulate you again on this defense. We think that you gave a very nice overview of your contributions, which form a very broad and impressive portfolio, and they result from a very extensive journey that you made through various fields. The fields of signal processing, machine learning, indexing, hardware design. And this journey was conducted under the auspices of graphs and neural networks with inspiration from neuroscience. And this was a very nice overview. We also would like to emphasize that your contributions are very coherent and they have a wide breadth. They range from the design of new hardware for associative memories and deep networks to the proposition of new algorithms for the compression of large-scale neural networks, but also mathematical analysis of uncertainty principles for signals on graphs, or applications to computer vision and neuroimaging. What we found remarkable is that your presentation conveyed at the same time a broad and tutorial synthesis on your interdisciplinary contributions, but also, again, at the same time, deep insights and your very acute vision on the challenges that lie ahead for the future of these fields that are very competitive and very active. As a jury, we were also particularly impressed by the fact that your contribution that not only consists of ideas that are creative and innovative, but they also, you really care about pushing them to the point that they provide competitive algorithms for state-of-the-art challenges in AI. We are also very, very happy with the scientific discussion. It was rich, it was rigorous, it was very high quality. It clearly demonstrated your maturity, your creativity, and most of all, your passion about your work. We also noticed that you really work well in collaboration. You are experienced in supervising students, and yet you have not yet become just a manager. You really are involved in depth in the scientific advances. So for all these reasons, we believe that, we are convinced that you have all the qualities to supervise research. You're already supervising research at the best international level. So for all these reasons, we unanimously award you the habilitation to conduct research from the École Normale Supérieure de Lyon. Congratulations, Vincent.
Bravo.
Well, thank you very much for the kind words. Thank you, because of course, if I invited you, it's because you mean a lot to me, for your different contributions, for the discussions we had, for mentoring also my journey. And yeah, I'm very glad, very honored for all of that. So thank you again, and especially in these conditions. And I wish that I will be able to meet each of you in person soon to offer you a beer or something to thank you for that.
Thanks.
So it's always weird.
Yeah.
I think when we have these defenses online,
Yeah.
we don't know how to end. So I guess there's no other choice than just to leave at some point. But again, thank you very much for all of you, and thank you also to those who followed the presentation because it means a lot also to me. And have a nice evening, everyone, except Antonio. Have a nice day.
Okay, I thought you were going to fly your rocket and go away.
Yeah.
Okay, thank you. Congrats. Again, have a nice weekend. Bye-bye.
Bye-bye.
Have a nice weekend.
Bye-bye.
Bye.
And we'll find an opportunity to celebrate.
Yes.
Yeah.
Yeah.
Bye-bye.
Bye-bye.
Bye.
Bravo.